Good morning, everyone. Good afternoon, everyone. I am Angelo Roslinda, fourth year civil engineering student at the University of Mindanao. And we are here today for our subject CE443 Hydrology Code 5900. So I was tasked to report about the weather basics, focusing more on the atmosphere, its composition, characteristics, and stability. So let's proceed. So let's discuss first about the past and the future of atmosphere. Any atmosphere was present after Earth was formed around 4 billion years ago. It was probably much different than of today. Most likely, it resembled those of the outer planets, like Jupiter, Saturn, Uranus, and Neptune, with an abundance of hydrogen, methane, and ammonia gas. The present atmosphere did not form until after this primary atmosphere was lost. So there are theories that surfaced on how we came up with the present atmosphere. I have included three theories in this report. The first theory, it says that the primary atmosphere was blasted from Earth by the Sun. If the Sun is like the other stars of its type, it may have gone through a phase where it violently ejected material outward toward the planets. Second theory says that many of the gases in our atmosphere were ejected into the air by early volcanoes. At that time, there would have been little or no free oxygen surrounding the Earth. Free oxygen consists of oxygen molecules not attached to another element, like carbon to form carbon dioxide or hydrogen to form water. And the third theory that I have researched, it says that free oxygen may have been added to the atmosphere by primitive organisms, probably bacteria or and during photosynthesis. Photosynthesis is the process of a plant or other autotroph uses to make food and oxygen from carbon dioxide and water. Later, more complex forms of plant life added more oxygen to the atmosphere. The oxygen in today's atmosphere probably took millions of years to accumulate. So I have here a graph where we can see how O2 is produced billion years ago up until now in the present. In the graph, you can see that on the y-axis, it says that time before present, around billion years ago. Then on the x-axis is O2 as fraction of present atmospheric level. So according to the Britannica Encyclopedia, around 4 billion years ago, O2 is only produced by photodissociation. When you say photodissociation, it means that it is a dissociation of a chemical compound by the action of light. Then at around 3 billion years ago, the first appearance of oxygenic photosynthesis. Around 2.5 billion years ago, there is a survival of detrital urinanities, leaching of iron in fossil soils. Then at around 1.5 billion years ago, there is an occurrence of division of eukaryotic cells. At around 0.5 billion years ago, fossil animals' fuels, it is produced by O2 by circulatory system. The synthesis of collagen. Then we have the burial of organic carbon. So there is an O2 increase with that. Then the first fossil animals. So oxygen by diffusion. Then plants have evolved. So we came up with a 1.0. So that is what we are breathing right now. What is an atmosphere? The layers of gases surrounding a planet or other celestial body. It is one of the main components of Earth's interdependent physical systems. We live at the bottom of an invisible ocean, a layer of gases surrounding our planet. The atmosphere is so spread we barely notice it, yet its weight is equal to a layer of water more than 10 meters or 34 feet deep covering the entire planet. The bottom 30 kilometers or 19 miles of the atmosphere contains about 98% of its mass. The atmosphere Air is much thinner at high altitudes. There is no atmosphere in space. Atmosphere acts as a gigantic filter, keeping out most ultraviolet radiation while letting in the sun's warming rays. Ultraviolet radiation is harmful to living things and is what causes sunburns. Solar heat, on the other hand, is necessary for all life on Earth. So, composition of atmosphere. The atmosphere is actually very thin compared to the size of the Earth, equivalent in thickness to a piece of paper laid over a beach ball. That's how thin it is. However, it is responsible for keeping our Earth habitable and for producing weather. The atmosphere is concentrated at the Earth's surface and rapidly thins as you move upward, blending with space at roughly 100 miles above sea level. The atmosphere is composed of a mix of several different gases in differing amounts. The permanent gases whose percentage do not change from day to day are nitrogen, oxygen, and argon. Nitrogen accounts for 78% of the atmosphere, oxygen is 21%, and argon is 0.9%. Gases like carbon dioxide, nitrous oxide, methane, and ozone are trace gases that account for about 1/10 of 1% of the atmosphere. Water vapor is unique in its concentration varies from 0 to 4% of the atmosphere depending on where you are and what time of the day it is. In the cold, dry Arctic regions, water vapor usually accounts for less than 1% of the atmosphere, while in humid tropical regions, water vapor can account for almost 4% of the atmosphere. Water vapor content is very important in predicting the weather. Speaking of water vapor, let's delve a little bit to it. Water vapor is the most important greenhouse gas in the atmosphere. Heat radiated from Earth's surface is absorbed by the water vapor molecules in the lower atmosphere. The water vapor molecules in turn radiate heat in all directions. Some of the heat returns to the Earth's surface. Thus, water vapor is a second source of warmth in addition to sunlight. At the Earth's surface, water is constantly cycling through the atmosphere. Water evaporates from Earth's surface and rises on warm updrafts into the atmosphere. It condenses into clouds, is blown by the wind, and then falls back to the Earth as rain or snow. This cycle is one important way that heat and energy are transferred from the surface of the Earth to the atmosphere and transported from one place to another in our planet. So I have here a graph for the composition of Earth's atmosphere. So we have here nitrogen, which consists of 78%, oxygen 21%, argon 0.9%, carbon dioxide around 0.38%, 0.038%, then trace gases around 0.01%. Water vapor, as you can see, it says here that 0.0 to 4.0%. It is because, as I have said earlier, that water vapor varies on your location and the time of the day. So let's talk about the uses and abundancy of the three most abundant composition of Earth's atmosphere. First, we have nitrogen. Nitrogen is obtained by the distillation of liquid air. It is found as compounds in all living things and hence also in coal and other fossil fuels. Nitrogen is important to the chemical industry. It is used to make fertilizers, nitric acid, nylon, dyes, and explosives. It is used in the way to preserve foods and in the electronic industry during the production of transistors and diodes. Large quantities of nitrogen are used in annealing stainless steel and other steel mill products. Annealing is a heat treatment that makes steel easier to work. Liquid nitrogen is often used as a refrigerant. It is used for storing sperm, eggs, and other cells for medical research and reproductive technology. It is also used to rapidly freeze foods, helping them to maintain moisture, color, flavor, and texture. So the second most abundant is oxygen. Oxygen makes up 21% of the atmosphere by volume. The element and its compounds make up 49.2% by mass of the Earth's crust and about two-thirds of the human body. The greatest commercial use of oxygen is in the steel industry. Large quantities are also used in the manufacture of a wide range of chemicals, including nitric acid and hydrogen peroxide. It's also used to make epoxyethane or ethylene oxide, used as antifreeze and to make polyester, and chloroethane, the precursor to PVC. Oxygen gas is used for oxyacetylene welding and cutting of metals. A growing use is in the treatment of sewage and effluent from industry. And lastly, argon. Argon is the third most abundant atmospheric gas. Levels have gradually increased since the Earth was formed because radioactive potassium-40 turns into argon as it decays. Argon is obtained commercially by the distillation of liquid, same as the oxygen and hydrogen. Yeah. It is also used by welders to protect the weld area and in incandescent light bulbs to stop oxygen from corroding the filament. Argon is used in fluorescent tubes and low-energy light bulbs. A low-energy light bulb often contains argon gas, and mercury. So let's proceed to the layers of the atmosphere. This atmosphere has a layered structure. From the ground toward the sky, the layers are the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. Another layer, called the ionosphere, extends from the mesosphere to the exosphere. Beyond the exosphere is the outer space. The boundaries between atmospheric layers are not clearly defined and change depending on latitude and season. So, troposphere, the layer in which we live. The lowest layer of the atmosphere, which lies next to the Earth's surface, the troposphere, is also the densest atmospheric layer. It contains almost 90% of the atmosphere's total mass. Almost all weather develops in the troposphere because it contains almost all of the atmosphere's water vapor. Clouds, from low-lying fog to thunderheads to high-altitude cirrus, form in the troposphere. Air masses, areas of high pressure and low pressure systems, are moved by winds in the troposphere. These weather systems led to daily weather changes as well as seasonal weather patterns and climate systems such as El Nino. On average, the troposphere extends from the ground to about 10 kilometers high, ranging from about 6 kilometers at the poles to more than 16 kilometers at the equator. The top of the troposphere is higher in summer than in winter. Air in the troposphere thins as altitude increases. There are fewer molecules of oxygen at the top of the Mount Everest, Nepal, or for example, than there are on a beach in Hawaii. That is why mountaineers often use canisters of oxygen when climbing tall peaks. Thin air is also why helicopters have difficulty maneuvering at high altitudes. Stratosphere, home of the ozone layer. The atmospheric layer above the troposphere. Gases in the stratosphere are layered and do not mix as much as gases in the troposphere. The air is also very thin in the stratosphere and contains little moisture. The lower stratosphere is extremely cold. Its temperature averages around negative 60 degrees Celsius. But temperature rises as altitude increases in the stratosphere. The rise happens because ozone in the stratosphere absorbs ultraviolet radiation from the sun, a form of oxygen that prevents harmful UV rays from reaching Earth, which warms the air. Almost all of the ozone in the stratosphere is contained in the ozone layer. The region within the stratosphere where this thin shell of ozone is found is called the ozone layer. The stratosphere is crucial to life on Earth because it contains small amounts of ozone. The stratosphere's ozone layer is uneven and thinner near the poles and the amount of ozone in the Earth's atmosphere is declining steadily. Scientists have linked use of chemicals such as chlorofluorocarbons to ozone depletion. The ozone layer protects life on Earth by absorbing harmful ultraviolet radiation. Mesosphere, the middle layer. The mesosphere extends from stratosphere, the upper boundary of the stratosphere, to about 85 kilometers above the surface of the Earth. Here, temperatures again begin to fall. The mesosphere has the coldest temperature in the atmosphere, dipping as low as negative 120 degrees Celsius. The mesosphere also has the atmosphere's highest clouds. In clear weather, you can sometimes see them as silvery wisps immediately after sunset. They are called the noctilucent clouds or night shining clouds. The mesosphere is so cold that noctilucent clouds are actually frozen water vapor. Ice clouds, shooting stars, the fiery burnout of meteors, dust, and rocks from outer space are visible in the mesosphere. Most shooting stars are the size of a grain of sand and burn up before entering the stratosphere or troposphere. However, some meteors are the size of pebbles or even boulders. The outer layers burn as they race through the mesosphere, but they are massive enough to fall through the lower atmosphere and crash to the Earth as meteorites. The thermosphere is the thickest layer in the atmosphere. Thermosphere, the edge of atmosphere. The thermosphere is the thickest layer in the atmosphere. Only the lightest gases, mostly oxygen, helium, and hydrogen, are found here. The thermosphere extends from the mesopause, the upper boundary of the mesosphere, to 690 kilometers above the surface of the Earth. Here, thinly scattered molecules of gas absorb X-rays and ultraviolet radiation. This absorption process propels the molecules in the thermosphere to great speeds and high temperatures. Temperatures in the thermosphere can rise up to 150 degrees Celsius. Though the temperature is very high, there is not much heat. How is that possible? Heat is created when molecules get excited and transfer energy from one molecule to another. Heat happens in an area of high pressure. Think of water boiling in a pot. Temperature is different from heat. Temperature is a measure of the average energy of particles in motion. Exosphere. The fluctuating area between the thermosphere and the exosphere is called the turbopause. The lowest level of the exosphere is called exobase. The upper boundary of the exosphere, ionosphere, merges with the interplanetary space or the space between planets. Many weather satellites orbit Earth in the exosphere. The lower part of the exosphere includes low Earth orbit, while medium Earth orbit is higher in the atmosphere. The upper boundary of the exosphere is visible in satellite images of Earth called the geocorona. It is the fuzzy blue illumination that circles the Earth. Ionosphere, home of the auroras. In the upper mesosphere and the lower thermosphere, nitrogen and oxygen atoms absorb harmful solar energy. As a result, the thermosphere's temperature rises and gas particles become electrically charged. Electrically charged particles are called ions. Therefore, this part of the thermosphere is called the ionosphere. In polar regions, these ions radiate energy as shimmering lights called auroras. Ionosphere extends from the top half of the mesosphere all the way to the exosphere. This atmospheric layer conducts electricity. So we have discussed about the Earth's atmosphere. How about the atmosphere on other planets? So let's discuss about the extraterrestrial atmosphere. All of the planets in our solar system have atmosphere. Most of these atmospheres are radically different from Earth's, although they contain many of the same elements. The solar system has two major types of planets. The terrestrial planets includes Mercury, Venus, and Earth and Mars. And the gas giants, Jupiter, Saturn, Uranus, and Neptune. And last to be discussed, the atmospheric stability. Atmospheric stability determines whether or not air will rise and cause storms, sink, and cause clear skies, or essentially do nothing. Stability is dependent upon the dry and saturated adiabatic lapse rates and the environmental lapse rate. So I have here pictures. So in each instance, we have a parcel in contact with surface. Remember the rule. Air takes on the characteristics of the surface beneath it. In each case, then a parcel is formed with the same temperature characteristic as the underlying surface. To accurately determine the stability condition, we must follow this rule. First, always compare the parcel's temperature to that of the surrounding environment, not the other way around. So here in our first picture, if an air parcel is cooler than its surrounding environment, then it will be denser than its environment and will sink. Think of this situation as a pebble sinking in water. This is a stable air, which generally leads to clear skies. Then second, unstable, non-stable. If an air parcel is warmer than its surrounding environment, then it will be less dense than its surrounding and will rise like hot air balloon. This is unstable air and has the potential of creating storm. Last image, if an air parcel is the same temperature as the surrounding environment, then the parcel will not move of its own accord. This is what we call neutral air. So that's it for my report. Thank you for listening and God bless.